Welcome to the Cycle World podcast. I'm Mark Hoyer. I'm with Kevin Cameron, our technical editor. Today we're going to talk about how consistency is everything. Now, we've been in the combustion chamber a bit lately, and we're going to kind of stay there because consistency is everything. Right, Kevin?
Well, you'd like it to be,
Yes.
but it's an interesting story, and it goes back 250 years. Because
This is gonna turn into a drinking game. Like if it starts before 1940, is 100 years? Do we take a shot? Go ahead.
there, James Watt sort of pushed the idea of the steam engine as using steam pressure, whereas the earlier steam engines had used the vacuum created when steam condenses. Newcomen's mine pumping engine was a condensing engine. And he got to thinking, well, there's a lot going on here. There's friction and there's throttling loss and all these things that are happening. Wouldn't it be good to know how much work the steam is actually doing? So what they did was they attached a device to the steam cylinder which pushed a pencil in a linear fashion, in a straight line, with the distance from the origin being proportional to the pressure in the steam cylinder. And they rested the pencil on a card, which through some mechanism was made to move back and forth in proportion to the motion of the piston. And they found that this drew a closed figure which revealed the pressure in the steam cylinder. And that is called, to this day, because such devices are used on internal combustion engines, indicated pressure, and rather than brake pressure. Brake pressure is measured on a brake on a dynamometer, but indicated pressure is when you measure the pressure in the cylinder itself. So this wonderful device was invented. It remained secret for about 100 years. And when the internal combustion engine came along, the steam version with the moving card by that time had turned into a drum that rotated this way and that with the pencil bearing against it. But the idea was the same, to draw the curve of pressure through a whole cycle. So they tried to build these things for early internal combustion engines, and an early mentor of engine pioneer Harry Ricardo, name of Bertram Hopkinson, came up with an optical indicator. Instead of having rods and levers, he would use a light beam to to turn the pressure in the cylinder into a moving spot. And here is the point of all this palaver. When they recorded one after another trace from combustion going on at a steady rate in an engine on the dynamometer, they found that they were not all the same. Some of them were notably better than average, some worse than average, but with a Gaussian distribution, most of the combustion events were in the center of the graph. The Gaussian distribution is one that starts at zero, rises in a sort of haystack fashion, then comes down as asymptotic to zero at the other end. And out here at the extremes are the ones that are better than average and the ones that are worse than average. Now, here's the thing that irked people when they looked at these graphs. They said, if we could make every firing cycle of this engine as good as the best ones that we've recorded, we might have as much as 20% better performance. Well, what was varying? Peak pressure was varying. Also, the location of peak pressure, as if someone was twiddling the timing behind your back. So this has
you mean the location of peak pressure as it relates to
crankshaft angle. Yes, sir.
position. Yeah.
Normally, if you look at the piston position graph, it looks a little bit like a sine wave. But near the top of the graph, the piston doesn't move much. It's a sort of rounded hilltop. It's not pointy at all. So it's desirable that peak pressure should occur just before the piston sort of takes a dive. You don't want peak pressure being held up against the cylinder head by the piston when it isn't moving very much. So it's desirable that peak pressure should occur somewhere around 11 degrees after top dead center. Okay, so they look at this and they're thinking, what can we do about it? So in the 70s and 80s, they did so-called parametric studies. They tried to think up all the things that could possibly be affecting this variability. And they didn't come up with any improvements in the consistency of one cycle to the next. That is, they did not make a dent in cycle-to-cycle variation.
And that's the foundation of what we're talking about is cycle-to-cycle variation.
Yes.
Kevin's spent it, his lifetime thinking about it. I have to some degree as well. I first heard it from a Ducati engineer, and we were talking about it, and it was a very big bore. And I said, well, it's difficult to get good combustion in a big bore. And I was just, trying to ferret out more information. And he said, yeah, we did these things, and he listed off the shape of the chamber and removal of pointy things and stuff inside the combustion chamber in an effort to reduce cycle-to-cycle variation.
Yep. Now, to give an idea of the variability that exists in combustion, I want to go back to the days when the late Dick O'Brien, who was Harley racing manager in 1957 to 1984, and a man of salty speech, and
Best interview of my life. It was amazing.
His longtime friend, the late Don Tilley of Statesville, North Carolina, who had many friends in the NASCAR business, and he was a curious man. They were assembling the engine of Lucifer's Hammer, which was the Battle of the Twins bike that they had built, using a Harley engine as the basis. It's a 2-valve, 45-degree V-twin, just as God intended, as some folks might suggest.
Famed Milwaukee vibrator.
Yeah, yes, sir. And you can tell when this engine is running.
Yes, which we seem to like.
Yeah, yeah. So they're assembling this on fresh build. And, newly seated valves, some modifications, possibly fresh pistons and rings. And they make a dyno run, and the power's disappointing. And they check everything to make sure they haven't made a foolish mistake, because being humans, we sometimes don't turn the fuel valve on all the way. So the main jet migrates upstream to that valve. And they couldn't find anything. So O'Brien says, all right, we're going to have to dyno time the son of a gun. And with the engine running, he loosens the pinch bolt that holds the magneto at the desired timing and starts tapping on the side of it with a soft hammer, advancing it. Torque gets worse. Torque is dropping. Follows it up a little bit to make sure, yeah, that's what it's doing. The torque is dropping as we advance the timing. So then, okay, wants it go in the other direction, that's what we're going to do. Tap, tap, tap. As they retarded the spark, the torque went up, 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 and finally they found they reached the sacred goal called MBT, minimum for best torque, and it was at just over 26 degrees before
That's
top center.
amazing. Tell us why that's
Wonderful.
amazing. Yeah, I mean, it's
Because normally a big old two valve cylinder will fire somewhere between 32 and 36 degrees, unless it has a really ugly piston dome that is basically saying to the flame front, stop and go no further. And so they're looking at each other like, we've learned something today, only we don't know what it is. So they're on the West Coast a while later, and they run into Bobby Stallman, who was for many years the champion man at the races. And that includes champ cars,
champion spark plugs.
champion spark plug.
We don't
Yes, sir.
we don't have a spark plug guy anymore, do we? It's too bad.
Yeah. Well, because people don't see spark plugs. They're not removed. They just stay in the engine. And so they tell Stallman this story. And he looks at them in a jolly sort of way and he says, you fellas are really lucky. This will happen. This happens every now and then. And when it does, you just have to count yourself lucky and see if you can reach around, give yourself a pat on the back. He says, and, we don't know what's going on. We just assume that when the spark passes and it ignites a flame kernel, that flame kernel goes in exactly the right direction to bring the fiery message to all parts of the cylinder combustion chamber pronto. Well, you were going to say?
Well, it reminded me of Paul Dean, our longtime service editor, and every role Paul had here.
Resident adult sometimes.
Resident, absolutely, and truck driver, you name it. Like great mechanic. He, in his spare time, was part of a dirt track car racing team. Big 800 horsepower V8s and stuff, and he indexed the plugs for that. So he made the electrode face, the open part of the electrode face the way that he felt it should. Then you use different shims so that the rotation of the plug when it's tight puts it in the position that you want.
Yep.
And I want to say he said something like 5 to 10%, something along those lines, just indexing the plugs for that engine. A big improvement, let's put it that way, just for orienting the plugs in the way that the spark would set the kernel on fire and watch it go,
Yep. Now, one of the things that sheds light on what we're talking about is the FEMSA company in Spain around 1968 were preparing their FEMSAtronic ignition as a replacement for the magnetos that were supplied on Yamaha production racers, TZ250 and TZ350. And one of the problems with the magneto was that you set the timing perfectly, get the gap just right, start the engine, let it run for 2 seconds and shut it off, check the timing again, it would be different. Because out on the end of the crankshaft is the cam that is opening and closing the points. And this thing is rattling and banging and clunking around. It was the best that could be done in 1964. And it kept on for another 10 years, pretty much. So FEMSA are testing their electronic ignition, and they found that on two-stroke engines, it basically, engine wouldn't run. Couldn't start the engine. And they had all the test equipment that you could imagine. A spinner, you could bolt your ignition to it just like it was an engine, had a back plate like an engine, and it would spin the ignition, and you could look at the sparks, and you could put your oscilloscope on and watch the ionization of the gap and the 40-volt continuation once the spark was established. So they're looking at this and they're thinking, we've built a modern ignition. Modern ignitions only have the gap breakdown voltage spike, which may be 15,000 volts or more.
It's more now.
Yeah. And
Back
then,
in, yeah,
well,
back
the
then.
gap may break down at 14 or 15,000,
Yeah,
but the
fair,
thing
fair
is
enough.
capable of, yeah. So what if they're saying this is a two-stroke engine? When the transfer ports open, there has not been an exhaust stroke which has pushed the exhaust out. The exhaust is still there. So the transfer flow is coming into the cylinder and mixing with residual exhaust gas. So they're saying, what if a little packet of exhaust gas is passing through the spark plug gap at the moment of the spark?
Inert.
Misfire.
Yeah,
Yeah.
inert gas. That's why we do EGR. They pump burned air fuel. It's inert. They put it back in the cylinder at part throttle, and it cools off everything, so you don't get your NOx up.
Yes. So this then this will move us on to another part of the narrative in just a moment. But what they did was they made their spark discharge more like that of a magneto. And the same thing happened when electronic magnetos were built for top fuelers. Top fuelers have hellish conditions in the combustion chamber with blobs of fuel flying around.
Has it not been said that on the top fuel dragster that the cylinder is practically filled with fuel?
Yeah, it's a lot of fuel. And when they extended the arc duration, it gave a much longer opportunity for the right little packet of just correct mixture to pass through the spark. I should call it the arc, because it's sitting there going like a welder. You may have used a welder that uses a voltage spike to establish the arc. Old time welders are tapping with the end of the rod to try to get it to ionize the gap. But that voltage spike does it for you, and then you're just going buzz. And if you look at the discharge, it goes up to thousands of volts to break down the gap between the tip of the rod
Oh,
and the work.
it's a miracle on the TEG machine I have.
Yeah.
It's oh.
And then it falls back to 40 volts. And that's just what happens in a magneto ignition. So they had to make the Femsatronic mimic a magneto, and it worked fine. And thousands of people bought those FEMSA systems and put them on 2 strokes and 4 strokes, and same with the German Krober ignition.
Well, my practical experience with this in dynoing thousands of motorcycles here over the last many years, a fellow who was land speed racing in Indian wanted to dyno his flathead Indian, old stuff. He wanted to dyno his bike here, and of course I said yes, because I want to see that.
Yes.
I definitely want to be a part of that.
I will hold the door for you.
Yeah. So we put him up, strapped him in, and we fired it up. And his magneto, genuine magneto, I don't remember the brand, but it's one of those gigantic things.
Yeah.
The RF coming off of that was impossible. The screen of the computer was doing like waves, and it was
wonderful.
And so he's just using giant copper cables, and the signal is ringing back and forth in those things. And
it's an antenna. Yeah.
It's just, it was really hard to get a clean number. We were getting like gaps of a curve. The computer's like, "What are you doing to me?" And
time for a tinfoil hat for the bike.
Yeah, absolutely. And so we, all these modern ignitions just go, and that's kind of it. They've got suppressor wires, and they've got resistor caps and things that gaps between, inside the plug. And anyways, interesting practical demonstration of radio waves happening.
Yes.
And how long it would go on.
That's the reason why modern ignitions allow only the capacitive part, that is the electricity that is stored on the wire itself, on the conductor. It goes up to a tremendous voltage. The gap in the spark plug is ionized. It breaks down. That capacitive part rushes across the gap, and the resistor wire or the internal gap or whatever just says stop, and the inductive part of the spark does not occur. The welder, the 40-volt welder arc. So now we turn to the 2 volumes of The Internal Combustion Engine in Theory and Practice by Charles Fayette Taylor, who lived to be over 100 years old. When he was 23 years old, he had been put in charge of the U.S. Army's Air Development Center at McCook Field in Ohio. And the way he tells it, he said, there I am, I'm in charge of this big operation, and all I have as knowledge of technology is hearsay. There is no body of knowledge. So he quit that job and went to MIT and eventually established a department that the Sloan Automotive Lab, which is still going. So in that book, he describes his view of what combustion is. Now, the piston is descending on the intake stroke. It takes time for the mass of air and fuel in the intake pipe to accelerate. Finally, it catches up. It's just coming in at a tremendous speed, hundreds and hundreds of feet per second. And that energy goes into the cylinder and will be intentionally stored by one of 2 methods. The first one is axial swirl. If you look down on the cylinder like this, a tangential intake port causes the material to circulate in there.
Hose on the side of the bucket, as you always say. Play
Yes,
with
the hose
run it
into the bucket.
Side and make the swirl happen.
Because there you are waiting for the bucket to fill, and it's taking forever. So you play a game, and that's the game. Anyway, swirl, axial swirl, swirling around the cylinder axis. And the other one is, if we imagine the cylinder standing upright here, the flow comes in, goes to the opposite cylinder wall, down to the piston, and they initially called this barrel motion. Today it's called tumble. It's around an axis at 90 degrees to axial swirl, but it stores intake flow energy. Why are they storing it? They're storing it because as the piston rises, that vigorous motion, which begins at several hundred feet per second, is being crowded into a progressively smaller and smaller volume. And I have played little games while waiting for spaghetti to be done, depending upon sometimes making a portion for 1 person, sometimes for 4 or 5. And when the water is deep, which is when the piston is near bottom dead center, a single cell of motion develops. It's rising on one side of the water, the spaghetti pot, and it's sinking on the other. And with less fluid in there to make a smaller portion of spaghetti, it's easier for it to make 2 or more cells, because it's difficult to have material going one way on the floor of a shallow filling and the other way immediately above it, because what tends to happen is as they sort of rub against each other, it creates little vortices. So what happens as the piston approaches top dead center is that this large scale motion that we've gone to some trouble to create using intake flow energy breaks down into little turbulent cells. Now, Professor Taylor suggests that one of those cells is ignited by the spark. And he sees the cells as being lots of little gears that are engaged to each other. That cell has to turn 180 degrees to light the cell that's behind it, and that one in turn, and so forth. So, according to this model, the speed of the flame is less than, but related to, the intake velocity, because that's where all the energy is coming from. But instead of going straight across in a straight line, it's traveling by way of these various vortices. Some of them are lighting up their partners and others are fizzling. They're like lots of little small businesses starting up. Can they pay their bills? Well, a lovely phrase I found yesterday looking at my notes, which was exponential sensitivity to initial conditions. In other words, the butterfly effect.
Chaos theory, man.
Yes, indeed. And this is about as far as the research got up until maybe the mid-90s, because the development of engines up to that point centered on chemically correct mixtures, so-called stoichiometric. Memorize that word. It'll knock your buddies flat next time you gather at your favorite watering hole. Stoichiometric. Gotta love it. It just means complete the mixture that leads to complete combustion. So there's no leftover oxygen, no leftover hydrocarbon. It never happens, but that's what the ideal that you're seeking. So as long as they were working with good mixtures, when they looked at the phenomenon of cyclic variation, all they saw was chaos. They said, there is no deterministic element here.
That's just sad, right? Like, no, we can't. We just have to guess.
Yeah, we just have to say, well, a lot of stuff happens now that we don't understand, and we don't see a way to figure it out, so we'll move on to the next topic. Now, in the effort to meet emissions and to reduce fuel consumption, the automakers and the universities that depend on them for some of their funding began to work with lean mixtures or with stratified charge. Now, the problem with lean mixture is that hydrocarbon fuel and air is ignitable over a fairly narrow range. Anything richer than 10 parts of air to 1 part of fuel doesn't ignite. 18 to 1 or leaner doesn't ignite. And combustion slows down as you move away from stoichiometric, whether you're going lean or rich. So slowing down combustion is the same as retarding the spark. Down goes the torque. Oh, we're losing out here. Well, once they began to study cyclic variation in mixtures or circumstances in the combustion chamber that were closer to instability, now it fires, now it doesn't, don't we want to know the reason why? They began to apply chaos theory and modern data processing, and they came up with the conclusion that yes, there was a strong chaotic element, but there was also a deterministic quality. There were some things that could be controlled that would have an effect on cyclic variation. For example, they looked at the amount of exhaust gas that is left in the cylinder just before ignition. Why is there any? because when the piston rises on the exhaust stroke, it doesn't go all the way up and touch the head and chase everything out of the cylinder. There's the clearance volume there. It's full of exhaust gas. In the good old days, when we were allowed to use all the valve overlap we wanted, we could cause a sound wave to arrive in the cylinder that would start the intake process ahead of time. It would whisk out all of the residual exhaust gas and begin filling the combustion chamber with fresh charge. But of course, the EPA didn't like this at all, because where is that fresh charge, which is mixing with the exhaust gas? Where is it going? It's going out the exhaust valve. And that's why modern four-stroke motorcycle engines have shorter timing, which mainly means no valve overlap. Don't have the exhaust valve waiting to close until somewhat after top dead center, and the intake valve beginning to lift. So why are these modern engines why do they give such broad torque? Well, that's another story. But right now, what we're looking at is getting rid of valve overlap doesn't get rid of that residual exhaust gas at top dead center the way valve overlap used to do. So not only how much of that exhaust gas is there, there's the question of how hot it is. Because there are pre-flame reactions that occur in air-fuel mixtures as they get hot. These pre-flame reactions don't necessarily lead to hot combustion. It's just that action starts. It's like there's tension in the bar room, but it's not a brawl yet. So,
Well, making spaghetti last night, listening to the pot, I had the lid on because it heats up faster, heats the water faster.
Sure.
You hear the sound before it boils.
Yeah.
So you're hearing the water, and it's
something's happening.
They're like, I think I want to let go. And you lift the lid, and you're like, oh, we're ready to make spaghetti. And it's just tiny bubbles, but there's no action yet.
No action yet.
I put it back on. I turn around, I get the tomato sauce or whatever. And I'm like, what? And you lift it up, and it's going.
Yep. It's going. So this business with lean burn engines has brought us to this situation where they're trying very hard to control cyclic variation any way that they can, and they discover that they can, with suitable analysis of where the peak pressure is occurring and certain other things, they can adjust the timing from one cycle to the next in a way that anticipates sequences of events that lead to some part of the cyclic variation, and they can suppress it.
I have an ignition on my Jaguar cars, vintage Jaguar cars, called a 123 ignition, electronic ignition, and it has a mode. It does a thing that's cylinder balancing. And I don't know how it works, but I put that thing in addition to being able to control the curve and control detonation. For me in the mid-range, it's a hemispherical head, and they detonate at 1800. They just do. If you, with even messing with the curve and stuff, it's different. And anyway, you put that in, and idle improves. They have an inverted curve on the bottom end. Well, you can program the inverted curve so that it advances the timing if the RPM drops, and then you can stabilize your idle further in that way. But it also has cylinder balancing, about what you're talking about, minorly altering the timing based on what it's sensing in terms of RPM variation.
In a feedback way.
Yes.
Yes. Looks at what happened in the previous several cycles and says, aha, here's what I'm going to do.
And
And
from from you're the brain perspective thinking about all of this. From the consumer perspective, I'm also thinking about it, but I'm just delighted that I could buy that at an affordable price, and that people are applying this. It's just like the Ignitec ignition for the Ducati, being able to program that and have a curve instead of just a switch. A lot of early electronic ignitions were 10 degrees and then 35 or whatever.
oh yeah, that if you're right at that RPM, is it doesn't know which one to do.
Oh God! And you try to jet around it as I did on my Laverda on the
Not going
Dyno,
to happen.
and I'm like, "What is this?" And I tried every pilot. I had needles and cutaways and accelerator pumps because they're Delortos, and I'm on, as I've joked before, the needle exchange program with Ron Wood Racing because he had all the carbs, all the Delorto parts, and yeah, you just
Well,
infuriation. Yeah.
back when Mark Dobeck first offered the Dynojet Dyno, I think it was $10,000, which is radically cheap for a dynamometer setup. What it did was it put dynamometers into the hands of thousands of people who otherwise would have been no closer to a dyno than the pages of Hot Rod Magazine or Cycle World. And every problem that these people had with their engines was they could study it on the dyno, and they tried, like you mentioned, tried to jet it out of there. It's natural for a 4-into-1 exhaust system on a 4-cylinder engine to produce a flat spot somewhere below peak torque. And the cause of the flat spot is the pressure wave that I referred to a moment ago that comes back and starts the intake process by pulling intake air through the just closing exhaust valve, and the just opening intake valve clears the combustion chamber. Well, where am I now?
Well, this is the birth of the 421.
Yeah. Instead of that wave coming back, which is negative, at some lower speed, the waves alternate in the pipe. At some lower speed, it's a positive wave, and it pushes exhaust product back into the combustion chamber. And yes, it plays hob with torque. Torque falls. So these people are all phoning Mark up, and they're saying, "Man, something's wrong with this dyno."
Yeah, absolutely.
And of course, what was happening was the dyno enabled them to see it, and on a graph they could see it.
Well, and you don't have to ride the bike. That's the beauty of the dyno, is I could run at the RPM with my bike stuttering at 3,000 or whatever it was.
Mm-hmm.
And it's not moving, and I'm standing next to it, and I got my earmuffs on, and we're getting data. Like we're understand there's a sniffer on that dyno. I wish I'd used it. So, well, actually,
and of course,
we didn't have it on that dyno. It's
what you get from the rider is hearsay. What you get from the dyno is data. Now, you can also get data from riders, but so often, as in this Mark Dobeck case, they had just tolerated this flat spot.
You misinterpret it too. You think, oh no, man, this thing pulls like a train up top.
Yeah.
No, not really. It's coming on so quickly. The horsepower spike, the torque spike is so big once it gets into the happy zone. You think
also, because it's climbing out of that flat spot, it's really impressive.
Right. It's like, oh yeah, this thing gets hard, man. That's awesome, but it's way slower.
Yeah. So, incidentally, if you do a cam roll, and you basically scissor the intake and exhaust cams, this timing between these 2 points up here is the valve overlap. And if you scissor it out like this, you're allowing that negative wave to operate over a broader range and to have a stronger effect, because there are larger orifices available for the motion of charge. And the trouble, though, is that it just as it helps you more at the torque peak, it hurts you worse at the flat spot. So this is something that old timers people like Don Tilley used to go for the moderate, also dirt trackers, rather than, oh man, but the power numbers are like dynamite.
104-year-old Ed Iskandarian, recently interviewed on video, said that he made his name in the early days of making camshafts. No one knew what they were doing. He thought he was waiting for someone to tell him how wrong he was.
And nobody knew enough to do it.
Right. And he started making these cams, and he realized, he's working with the stock cam, and he found this recipe of opening rapidly without a lot of overlap, but opening and closing rapidly. And he got a cam that worked, that didn't wreck the valves and didn't wreck the springs and all of that.
It didn't wreck the drivability.
And he put an ad out, and he sold some to some guys in, North Carolina doing dirt track or whatever. And he started getting orders because he was making torque.
Yeah.
Yeah. That's pretty cool. It's the same lesson we learn over and over again, I guess. We keep discovering new things, or we try 5 valves, or you're trying all these different things as we're working to progress. I wanted to talk about the dyno. That suddenly all these people have a dyno. To me, that's the GSXR 750 effect.
Yes.
Which is mass sale of a thing that everybody just has to try to improve. Right? Like, we're out to race, and now we have this mass of people racing GSXR 750s in 1986.
Yep.
And what are they doing? Product development. Yeah. And all the answers you have, it's just like great combustion. Everybody's working on it at once, and the message spreads. It's just really cool. And doing that with the dyno, I think it's reflected today in the technology, the 3D printer. I can get a 3D printer and I can start making prototype parts in my house. I can get a water jet. I can take my chintzy plasma cutter and hook it up to a plotter, basically. And that plotter will cut near perfect parts. No more me oxy with the acetylene blowing out all over my shop trying to get the cutter to go, and then hitting the gas and
Yep.
Yeah, it's pretty neat.
Yes, indeed. So there is another combustion system, and I'm not speaking of diesel. In the case of diesel, the piston draws in an unthrottled charge of pure air. There's no fuel associated. There's no throttle. There's no air throttle. So the diesel engine is pulling in a cylinder full every time. It compresses it at a ratio of 16 or 17 to 1 so that its temperature rises high enough that when a fuel spray of number 2 heating oil, or functional equivalent, enters the cylinder, the first thing that happens is nothing. This is called ignition delay. All it is the fuel has to evaporate before it can form a vapor, which then can be heated up by the hot air to catch fire. Maybe 10 degrees. Anyway, that's the diesel cycle. This other thing is called HCCI, which is homogeneous charge compression ignition. Now, homogeneous charge means pre-mixed and completely mixed, not a mass of droplets in a mass of pure air with a fringe of vapor around each droplet.
Well, we've improved that through, initially we were working with carburation and needles and cutaways and flow.
Now we have 12 holes.
Right. And so you're relying on signal and lots of different things, pressure, all that happening. And so you're getting a charge that's a certain way. And carbs work great. Carbs can work extremely well. But we get a lot better results, as you say, with an injector that has very high pressure fuel, 1, 2, 3 bar, whatever they're running, and a duty cycle and which way are you aiming the injector still has an influence.
Yep.
Because if you instinctively you would say like, oh yeah, intuitively you would say, yeah, I want to shoot the fuel into the cylinder. But in fact, that has caused problems. Our own efforts with Project 156, the Victory race bike that we ran on Pikes Peak with Don Canay, we struggled with on throttle smoothness, rolling off to on, because it was not the combustion was inconsistent and it wasn't atomizing the fuel. And Victory had aimed them at the intake valves, the injectors, and when they turn them perpendicular to flow, the injector is perpendicular to flow, problem mostly solved, because it was being sheared apart. The spray was going across the port, and the
relative velocity was up,
and it mixed it, and it was closer to homogeneous. What you're saying, like, our ideal would be completely homogeneous charge, if we could ensure that every time, and that's what HCCI is.
And in fact, in engine testing, fuels testing, they use steam heated intake systems so that they can be sure that the charge is completely evaporated. But anyway, HCCI is a different kind of compression ignition, because here's what happens. The piston is rising. A fraction of hot exhaust gas has been, in a controlled way, allowed to remain in the cylinder. So as the piston rises on compression, it is raising the temperature of the mixture, just like pumping up a bicycle tire. The lower part of the pump, the tire pump, becomes sometimes quite hot from compression. Now, you add to that the heat of some exhaust gas that you have caused to be left in the cylinder, and what happens is pre-flame reactions begin to occur. Hydrogen atoms break off of hydrocarbon molecules, and they come tapping on the door of O2, which is a pair of oxygen molecules. They want to dance. These pre-flame reactions release heat at a low level. Compression moves along further, and if you have everything timed just right, in 1,000 points of light, as one of our former presidents said years ago, this pre-flame reaction begins to become hot combustion in myriad places throughout the cylinder, and you have a relatively smooth but rapid rise to peak pressure. No spark. And how do you change the timing? By controlling the amount of exhaust gas that is allowed to remain in the cylinder. Now, in 1995, Honda built an HCCI bike called EXP2, which in 95 finished fifth in the Paris-Dakar. It was a two-stroke, and when it's running, it just sounds like normal, except that it doesn't 8-stroke and 4-stroke.
Now, you should explain why that happens.
Yes, I'm going to do.
Okay, great.
First of all, there's almost no cyclic variation in HCCI. Why is that? In the case of spark ignition, you're igniting the charge at a single point and then gambling that something like the light up time that you are accustomed to having will actually occur. And the measurements have shown that it doesn't always occur, that it could be much better, but it could also be much worse. So that's something you'd like to play with, because if you could optimize that guy, you'd really have something. So in the case of HCCI, no cyclic variation, because ignition is dependent upon average conditions throughout the cylinder. And that's something we can control. The problem with HCCI is that on top end, you need a spark because there's so much fresh charge and so little hot exhaust gas that it cannot ignite. And an analogous thing happens at very low throttle. So there has to be a spark plug. It operates when in the regime of operation where it's needed. So initially there was a lot of interest in HCCI, and I think Mazda built something called Sky Active that was a four-stroke engine operating on the HCCI principle. But of course, what's happening now is that no one can be sure what the EPA is going to say, much less what's going to cause them to say it, because it's not clear when this all-electric thing is happening. People speak confidently about percentages of electric cars in the fleet by a certain period of time in the future. I think that what's happened now is that the automotive manufacturers have decided the main chance is we're going to be building combustion engines for a long time to come, so we'd better keep the research going into how to reduce emissions and fuel consumption. So, on the other hand, there is this gnawing worry that says, what if we get a bunch in Washington who really want this electric thing to happen right away, and we're stuck with all this investment in spark ignition R&D? Well, that's called risk. Supposedly, business, it doesn't exactly thrive on it, but as they say at the Kiwanis, people drink toasts of competition, but they phone Washington when they actually encounter it. So it's a hard problem for manufacturers of vehicles to know where they should stack their chips for the future. But it's always best to be prepared. So everybody's got an HCCI program. Several years ago, the SAE, Society of Automotive Engineers, came out with a fair-sized book, which was bound copies of the HCCI papers that were the most information packed that they had. As it turns out, HCCI goes way back in time. During World War II, the Russians wanted to come up with a knock-free combustion system that did not require them to have the refinery technology that the U.S. had at that time, the early 1940s. And so they did a bunch of research into this, into something very much like HCCI. It never came to, they didn't run aircraft engines on it, but that research is out there. And when two Japanese researchers sent the SAE a paper on this form of ignition, this form of combustion, at first the content committee said, this is incomprehensible. I don't know what they're talking about. And
awesome. I'd be proud.
yeah, the head of engineering at that time of Mercury Marine outboard motor makers, Ben Schaefer, somebody phoned, let's call Ben, he'll know. And Ben said, I want you to publish these papers because they are going to be very important one day. And here's why. So, well, geez, didn't know that. Okay. So there's a whole literature on this, and it's quite interesting to read if you care for that sort of thing. But on the one hand, you have HCCI where the point of peak pressure is determined by average conditions in the cylinder, so it is quite controllable. On this hand, we have the spark ignition engine, for which we have vast accumulated knowledge, but we can't eliminate cyclic variation because of that large stochastic, um, meaning mysteriously variable or chaotic component. The causation, we believe in causation. We're not talking about the quantum realm here where a proton and an antiproton pair can appear out of nothing. Well, that proton wasn't there before. We're talking about ordinary causation, cause and effect. It's just that there are so many of those little whirling vortices created as the piston crowds that large scale motion left over from the intake process into a smaller and smaller space. It breaks up into little turbulent cells. You light one of them on fire, you can't control the result. So, except when you do get some control when you get near the edge of stability. Very lean mixtures. Why would anyone want a lean mixture? I didn't know for years, and I had to give myself a little course. What happens is that the hotter that combustion is, the more energy of combustion appears not as the velocity of molecules in the gas zooming around colliding with other molecules, but in the form of molecular vibrations and rotation. Vibration and rotation doesn't push pistons. So the more intense combustion, the more energy is going out the exhaust valve in the form of energy that can't be used on the piston. So that incentivizes us, nasty business word that it is, it motivates us to cool off combustion so that we don't put much energy into molecular vibration and rotation. And that's what's behind this business of extremely lean combustion, because it's cool. It takes place at low temperature, and you don't get that waste of energy.
A lot of pilots still debate
fuel mileage.
Yeah,
Oh,
a lot of pilots still debate which side of highest RPM you want to set your mixture control on your aircraft, because if you don't fly older aircraft, they have auto throttles now where you can just do whatever you want and the engine takes care of it. But in your old Stinson 108 or your Cessna 170, you have the mixture control and you go lean of peak and it cools off. For some reason, the EGT goes down, and it's counterintuitive. Like you think, oh, lean's hot, we're going to melt the piston. And in fact, no.
Well, that's one that came out of course, the two-stroke experience. What happened was, well, first of all, let's look at what two-strokes were doing at the end of their period in GP racing. They had such good cooling, you could jet them down until they slowed down. And that's the natural state. But my 1965 TD1B 250cc Yamaha Twin is air-cooled. And that means it's not very well cooled, because the velocity of air passing over and between the fins is constantly varying. The level of power is constantly varying. So this is not a well-cooled situation. So what did we do about it? We ran rich, typically a couple of sizes. If you jet it down, power would rise, but so would failure. So we learned to associate lean mixtures with danger. But in fact, if you look at the stoichiometric conditions where chemically correct combustion is occurring, if you move away in either the rich or the lean direction, combustion temperature falls. And so what was happening with those early two-strokes was you were jetting toward a peak power mixture. And the engine didn't have the cooling to handle it. So exhaust
Well,
gas temperature.
if you were rich, you were also cooling the intake charge, right? That's what
Yep.
was happening. Yeah.
Well, when you take off in a big piston engine airplane, you enrich by about 20%. And the evaporative cooling that occurs when that extra fuel is sprayed into the supercharger reduces the charge temperature at the moment of ignition, making detonation a little bit less likely. So you can turn up the boost.
Toga, take off, go around.
Power. Oh, yeah.
Toga.
So that whole thing, some of those early engines, for instance, the engines in the B-29, 3350-23A, they had terrible mixture inconsistency around the engine, and it constantly changed as the RPM and the throttle setting was changed. Oh, this is the hot cylinder now. Oh, he's throttled back. Now this is the hot cylinder. So they could not set mixture on the lean side in order to extend range. In fact, those aircraft flew their missions on 70% power auto rich. And they used a great deal of fuel in the process.
I was just at AirVenture, and they have the two flying B-29s were at AirVenture.
Oh, both of them were there, yeah.
Yeah. Fifi and Fuddy Duddy, I think.
Doc,
yeah. Fifi and Doc. And they had the flight engineer and a pilot, and I was able to ask him a question, and I asked him about reliability, and he's like, I said, these were notorious for having a lot of problems and engine fires. And he's like, yeah, in fact, we had, it was not uncommon to get 100 to 300 hours out of an original B-29 engine. They
Yep.
weren't field repairing them. They were taking them off and replacing them. He's like, yeah, well, obviously we can't do that. So what we did is kind of a Frankenstein solution. And he said they took the core power unit off, like the Constellation. They weren't trying to get to 35,000 feet, so they didn't need dual stage supercharging. So they got the single stage off this other plane, and they got the accessory unit off of this other one. And now they have this incredible reliability. And
it's a post-war engine.
Post-war engine,
and it's a hybrid. Yeah.
Yeah.
And that engine, you can push the mixture to the lean side for extended cruise, because it has what they call spinner injection. The fuel is injected into the rotating supercharger impeller.
Yeah, it mixes it up.
And when you have consistent mixture getting to all cylinders, if you lean down, you're not moving some cylinders toward their peak and moving others down into the cool running stage where they don't make any power. So,
well, nonetheless, he said they calculate 500 gallons an hour for takeoff and 450 for cruise. So,
yeah. So, for the moment, there is not a lot of pressure on motorcycle engines to achieve the same low emissions that automobile engines are required to reach. And the reason for this is actually rational. It says automotive companies are very large. They have R&D funds that are equal to the task. Let them spend it. Motorcycle manufacturers are not noted for having endless research labs doing contingency work. Well, what if the EPA wants this? What if the German guys want that? We have to develop it ahead of time so that we won't be embarrassed when we're caught unawares. So it's not fair to exact the same level of emissions from motorcycle manufacturers with their relatively limited resources. So for the moment, motorcycle engines are not being driven into lean burn, stratified charge, and there are no standards for fuel consumption. So as long as that continues, there is no motivation to explore um, cyclic variation. Naturally, if the people at Ducati who enjoy R&D very much, as we've seen in MotoGP, if they come up with something that works, so much the better. But the thing is, cyclic variation was there in the beginning when carburetors consisted of a shirt wetted in gasoline stuffed into the intake. That was a carburetor. They called it an evaporator carburetor. We have cyclic variation today with the most sophisticated digital fuel injection. So the problem is continues to stare us in the face, but we're not under strong motivation to tackle it directly.
Yeah, our relative sales volume is also, at least in the United States. I mean, it's a different case in India, of course, or other Brazil. But here we're looking at probably 15 million automobiles sold every year versus,
Yep.
500 to 800,000 motorcycles, something in that range. So we don't have as large of an impact either, per mile, per capita, whatever you want to say about it.
And there are nearly as many automobiles registered in the U.S. as there are people. There's 335 million people and something over 280 million cars and light trucks registered. So that's the big difference between motorcycles and cars. Some extremists will say, "Oh, well, do you realize that your motorcycle emits as much this or that or the other thing as a showroom full of Cadillacs?" It's not relevant. It's not relevant. We don't expect people to put catalytic mufflers on their campfires. So,
Well, how much
for the
fuel,
moment at least.
how much fuel does a C-130 take to get off the ground?
Oh, yeah.
How long are
Sure.
we going to heat our house with that?
Yes.
So,
Well, I used to see the C5s that would land down south of me here. And I would think to myself, each time they take off for a long distance mission, they've got enough fuel on board to heat my house for 50 years.
there's Kevin doing the math. Well,
It's
in talking about,
arithmetic. It's
yeah,
arithmetic.
yeah. It occurred to me while we were talking about this, one of the things that would make HCCI great in certain applications is that it has that range of happiness where it's doing its HCCI thing. So if you're running a generator, or if you're running,
You would design it for operation at that point.
you
Sure.
run an aircraft with it, or a boat, where you're saying like, yeah, I mean, a boat, there are certainly sport boats where you're varying RPM and you're varying throttle. And our whole thing in motorcycles, I mean, everything that we seek is perfect application of torque, predictable, something that
Yes.
the rider's brain can get its head around, and we don't spike traction. We're on the edge, and we need everything to be perfect. Whereas if you're running a hybrid's not great, right? Because we're doing two power plants at once. But then maybe we can do something with a very small HCCI engine that's super efficient and very clean, and it's running,
At its
whatever,
best point, at best
at its best.
BSFC. Yep.
Yeah, and we're just motoring around town. We're not trying to win races or do wheelies or burnouts. We're just trying to get to the grocery store. Who knows? Well, cycle to cycle variation. We hope you enjoyed that. We enjoyed it, certainly. And to be honest, that's why we're here.
Yes, we like it because what they say about writers is their most important audience is themselves. They're writing to please themselves. And if it should please you, our readers or listeners, so much the better.
Yeah, the goal is clarity. That's clarity and learning. I mean, the reason I started to write things down was to try to own them.
Yeah.
try to understand and to own, and it forces you to organize your thinking. And I know we wander around and we have a lot of conversation here, and occasionally the listener will call me the Dunning-Kruger butthead or whatever, but get that guy to shut up. But I like to think I serve a little purpose here, so because I get to say thank you for listening and join us next time. This was the Cycle World podcast, and we appreciate you being out there. Get down in the comments, and we'll see you next time.